So, hello and welcome, student, for today's lecture. This is our MA415 Algebra and lecture number 37. Now, recall that we are discussing about field theory and we discussed about simple extension and then sub extension and relation among them. Okay, so there is something called extension generated by finitely many element. Okay, so let me just define. So other than simple extension, you can have, like, suppose you have field K and you can write down K is, say, if alpha 1 is alpha 2 something, if alpha n, so it's called and or a finally generated extension. Okay, a finitely generated extension. Okay, so there are finitely many elements which generate K over F extension over F. Okay, so this is also, you can think about that. For example, if your extension f of, say, alpha 1 alpha 2, you can also think this as f of alpha 1 of alpha 2. What does that mean? That means, so you first take the simple extension of alpha 1 and then you are taking an extension by alpha 2 over f of alpha 1, so that will be this. Okay, so this is the extension of that thing. Okay, so now you recall that we define a theorem that if simple extension is algebraic if and only if alpha is algebra if and only the simple extension is finite, right? So similarly, you can talk about the extension, not only the elements, about the extension. So you can say proposition. So you have K over F. So is finite extension if and only if so that time the simple extension f of alpha over f was finite, right? Now I choose K over f is finite if only what happened? K is some alpha 1 alpha 2 alpha n where alpha is are algebraic over f. So what does that mean? That means every finite extension over a field F is generated by a finitely many algebraic elements for F and vice versa. What does that mean? If you generate a field with finitely many algebraic elements over F, that field will be also finite. Okay, so the proof is also not so difficult, so let us discuss the proof. Okay, so two conditions. So let us first assume that let this dimension of K over F is finite, say something n. Okay, and obviously then so you have basis. So alpha 1 alpha 2 alpha n be a basis of K over F. Okay, so what I need to prove? I need to prove that these alpha is are actually algebraic over F. Now consider CC. Now for each I, that I equal to 1 to n, so what you can say that the field K is some extension of alpha I, and that is extension of F, right? And what we know that this degree that we proved last day, degree of k over f is nothing but k over f of alpha I, and then f of alpha I over f, right? This is okay. So for each thing, so you have this equation. So what does that mean? That means the degree of f of alpha I over f, that is actually finite, right? So this divides degree of this, which is finite, right? So thus so this alpha I over f, this degree is finite for all I, right? For all I equal to 1 to n. What does that mean? That means, recall in last lecture we proved that if the simple extension is finite, then alpha I must be algebraic. So thus alpha i's are algebraic, right, over f, which generates the basis of, so we generate k over f, right? So one part is obvious. Now conversely is also not so difficult. So conversely what I need to prove, so conversely let k equal to f of alpha 1, alpha 2, alpha n be an extension of f by algebraic elements, Okay, so what I need to prove? I need to prove that the dimension of k over f is finite. Okay. So now what I can write? We can write k equal to, so you understood that what is happening here. So you start with f, and then you're going to f of alpha 1, and then you're taking f of alpha 1, alpha 2, alpha 2, and so on, right? And k equal to f of alpha 1, alpha 2, alpha n, right? So now what you can say, you can say that so you start with this dimension of f alpha 1 over f. You know that this is finite, right? This is finite as alpha is algebraic over f, right? Now similarly you see that f of alpha 2 over f is also finite, right? F of alpha 2 over f is also finite, right? So f of alpha 2 is finite over f, right? So now what does that mean? If alpha 2 is finite over f, and then if we add these algebraic elements, okay, so if we add the algebraic elements f of alpha 1, then what happens? Then obviously you can say that this f of alpha 1, alpha 2 is also finite over f of alpha 1 is also finite for f of alpha 1, right? See, if alpha 2 is an algebraic element over f, right? So hence is also algebraic element over f of alpha 1 is also finite over f of alpha 1, right? As alpha 2 is algebraic over f of alpha 1, right? See, if some element is algebraic over a field, then it will be algebraic over any extension field of that field, right? So alpha 2 is algebraic over ft, and hence if this is this, so what does that mean? That means finally you can say that f of alpha 1, alpha 2 over this degree is what? This degree is nothing but f of alpha 1, alpha 2, and then f of alpha 1, and then product with f of alpha 1 over f, right? Now this is finite, hence this is finite. The product is also finite, right? Clear? Now do the mathematical induction, right? So you have in finally many algebraic element, and you know that everything is finite. So now using induction, we conclude that k equal to f of alpha 1, alpha 2, alpha n is finite extension. Finite means finite extension, I mean to say extension of f. Okay. So if you start with extension, if you find extension, it must be generated by finally many algebraic elements. Okay. So immediately you can have the very nice corollary. So this is the ends of the our previous proposition. Now what you can say here directly, you can say that if you choose say alpha 1, alpha 2 algebraic, choose any two element algebraic over a field if then their addition, multiplication, whatever you choose, alpha 1, alpha 2, sorry, alpha 1, alpha 2, and if the alpha 2 is non-zero, then you can take division also. If alpha 2 not equal to 0, okay, then they all are algebraic actually. Then these are also algebraic. So what does that mean? That means if you have algebraic element, and then if you add those things, take product or division, they become also algebraic element. Okay. So the proof, how to prove this kind of statement? So proof, and the proof is what? So you know alpha 1, alpha 2 algebraic, so you consider the k is f of alpha 1, alpha 2, right? Is finite, right? Finite as alpha 1, alpha 2 are algebraic element, and this we just proved in last theorem, algebraic over f, right? Now you have a finite extension, and inside f and also now you see that this alpha 1 plus or minus alpha 2, or alpha 1 into alpha 2, or alpha 1 by alpha 2, they are element of k, right? If alpha 2 not equal to 0, obviously the element of k, right? So thus this alpha 1 plus minus alpha 2, they are element of finite extension. Okay, so they are algebraic, because every element, so if k is algebraic, so k is finite extension, and every element of f is also algebraic, right? So are algebraic over if. Okay, so this is the proof. Whenever you have the algebraic element, the sum, product, division, or whatever, they are algebraic. And what you can say directly that if you collect so the remark, what remark you can say from here. So you start with an extension. Say for example, let say for example L over A be any extension let k is a subset of L containing all the algebraic elements containing all the elements which I rather say that containing all the elements which are algebraic over F. Okay. So what I'm saying, I'm taking elements of L which are all the elements which are algebraic over F. Okay. Then K is also a field. Then K is a subfield of L containing F, right? Because every element of F is algebraic over F itself. Because the dimension of, if we attach that element, it will be same field, right? Dimension is 1. And there are many other elements over K that may be algebraic over F. So this is a subfield because any two algebraic number, addition, subtraction, product, division, everything is algebraic. So they form a subfield, right? So algebraic element of any field over another field is always a subfield which is algebraic, subfield containing that, right? Okay, so maybe I will prove one more interesting theorem, and then we will go to the main idea. So I may not give proof of every theorem because I need to I don't have much time, so I need to give the idea only. Okay, so this is an important theorem, so that's why I'm just trying to write it. So suppose you have two extensions, for example L over K and K over F. Okay, and if you know that this is algebraic and then this is also algebraic, so you know the meaning of algebraic means every element of L over K is algebraic over K, and every element K over is algebraic over K, then this is also algebraic. Okay, so what does that mean? L over F is algebraic if you not leave L over K and K over F are algebraic. So one part is obvious. If L over K is algebraic, so every subfield will be algebraic. Because every element of L over K is algebraic, so every element of L over F is algebraic, so they will be algebraic over K also. Okay, because the polynomial they satisfy over F is also L polynomial over K, right? And also K over F is algebraic because element of K are element of L. Now conversely, the converse part you need to prove that conversely conversely let L over K and K over F we do algebraic extension, right? Now I need to prove that L over F is algebraic. So what does that mean? That means every element of L is algebraic over F, right? So let us start with the elements. So let alpha belongs to L be any arbitrary element, arbitrary elements, okay, as alpha is algebraic over K. What happened? So we have a monic polynomial, right? So alpha satisfy a monic polynomial. See, one question you can say that alpha satisfy any polynomial. Yeah, obviously when alpha satisfy any polynomial, you can find out monic polynomial also. So it doesn't matter. Okay. So or you can write down then alpha satisfies a polynomial over K, say like this, say maybe f of x equal to, let me write down, say a power a n x power n, so on, a1 x plus a0, something like that, okay, and f of alpha equal to 0, okay. So and these AIs are also elements of the field K, because this is polynomial over K, right? So once you have this kind of polynomial, then you can consider the field, this field. Now consider the field F, which is field extension of F generated by F and alpha, and then this A0, A1 and AN. Okay, so this is a subfield of, obviously this is a subfield of L, right? Because it contains L contains all the elements. So this is a subfield of F, and you know that okay. So one more thing, yeah. So you know that K over F is algebraic. So you can talk about you can write down this field as like this is an extension. Okay, so let me write down, this is an extension field over say A0, A1, AN, and this is obviously A0s, ANs are element of K, which is algebraic. So this is finite extension. This is finite extension over F, right? And then you can go over F. Okay. So what does that mean? That means now you have these two. This is the tower of extension, and you can talk about the dimension. Now this is finite, as these AIs are algebraic over F. Okay. Now what is this? See, this is also finite extension, because this satisfies a polynomial over degree n, right? So if alpha is algebraic over this, so this is also finite, as alpha is algebraic over this field, over this f of a0, a1 and a, right? So what does that mean? That means f of alpha over this is algebraic over f, that is finite. So thus this f of alpha comma a0, a1, an, and this is finite, right? The dimension is finite, because if you take the product of two finite things, it's finite. Okay. So what does that mean? That means so this finite means f of alpha A0 and N is algebraic, over F, right? Finite extension of algebraic, right? And what does that mean? That means this means that alpha is algebraic over F, right? So we started with the arbitrary element of alpha of L, and we showed that's algebraic over F. So thus L thus this L over F is algebraic. So what does that mean? If you start with, and so if you go and algebraic extension over another algebraic extension, then the final extension will be again an algebraic extension. Okay. Okay. So with that is idea, one can ask that what about does there exist an extensions where like every element is algebraic? Okay. And the answer is yes. So we can talk about an extension field over a field which is kind of every element of that field is algebraic. Okay. So, so there are two type of question can arise. So I need something called a extension which actually contain all the roots of a polynomial, and this kind of extension is called a splitting field. So let me define what is that splitting field, and then I will define that thing. Okay, so splitting field. So suppose you have a polynomial over a field F. So this is inside the polynomial ring. Okay, and so an extension K over F is said to be a splitting field of I should say I will tell you, because these are always isomorphic. Whenever it is split, they are isomorphic actually. Okay, but let me just write down splitting field of fx over f if fx split into linear factors in kx, what is that? Yeah, in kx, and not only that, there is no subfield of k. Splitting field is kind of a minimum field containing all the roots, you can say that. Okay, and there is no proper subfield of k over which so the split into linear factors is called split completely. Okay, over which fx split completely. So what does that mean? So I am saying that completely. I mean to say that this is kind of the minimum. You can think that, or rather you can say minimal, obviously, because they are isomorphic, they are up to isomorphic, so you can say minimum in that sense. Minimum field containing all the roots of the polynomial over a field f. Okay, so for example, you can, for example, you have this polynomial x square minus 2 over say q, and you see that the splitting field x over q is nothing but q root 2, as you can write down fx equal to x plus root 2 into x minus root 2 inside or over q root 2, right? Over q root 2, so this coefficient is element of q root 2, right? Yeah. Now let me ask another question. What about this polynomial fx equal to xq minus 2? Okay, what is the splitting field? Over q. So the naturally you may feel that okay, it should be kind of to the 1/3, right? And the answer is no. So this is not to the 1/3 because you see that this polynomial has complex root also. Okay, and so what does that mean? That means for example, what are the roots of this polynomial? Okay, so if you want to write it down, you can write it down. So if you write down okay, so you can write down that 2 to the power 1/3 cube, and then this is 1 cube also, right? So you can talk about the cube root of unity also, you can talk about, right? So the cube root of unity will play a role here, and then it will be having nothing but x minus 2 to the 1/3 is 1 root, and then x minus 2 to the 1/3 into 1, and then 1 has 3 cube roots, right? 1 and then omega and omega square. What is omega square? I will tell you one. Okay, so this omega, where omega is the primitive cube root of unity, cube root of unity. Okay, so this is like omega cube equal to 1 and 1 plus omega square equal to 0, right? Something like that. So and this omega is a complex number, right? So that does not belong to this field, so you need to add this also. So the splitting field of this will be this, and this is the smallest field. You cannot go down to any subfield where fx split. Okay, proper subfield. So this is an example, and then now again my question, I can come back to my question again. So my question was that whether such kind of field exists where every is extension of a field where every element is algebraic over the given field, and this is okay, this is true. So let me define two such definition, and one is also a field so F is called algebraically closed if it is the splitting field of all the polynomials in fx. So whatever polynomial you choose in fx, if f is the splitting field of all those polynomials, then f is called the algebraically closed. Now what does that mean? That means any degree polynomial over f split completely over f, means you can add linear factors over f, right? For example, see the field of the field of complex numbers is algebraically closed. And this is also called fundamental theorem of algebra. This is also called the fundamental theorem of algebra. Theorem of algebra. Okay. And with the help of this I can define something called algebraic closure. So so definition. So let A be a field, the algebraic closure of F is the field. So what the field say bar, we write down by this symbol F bar, satisfying this following property, satisfying the following properties. So what are the properties? So property number 1. So first, F bar is algebraically closed. This first property, algebraically closed. Okay. And second property is what? The second property, F closure is algebraic over F. Is algebraic over F. Okay. This kind of field is called algebraic closure. And so what does that mean? That means every element of the field is algebraic over F, and also whatever polynomial you choose over F bar, all the roots belongs to F bar, right? Okay, so like C is algebraically like R closure is C. Okay, this is an example. Okay. And Q closure is a set of all algebraic elements. So this is called algebraic number fields. What is called field of algebraic numbers. So okay, I should say field of algebraic numbers. So field of algebraic numbers. Okay. So this is what this you collect all the numbers which are algebraic over Q. So this is a field of C containing all the numbers which are algebraic over C. This is Q bar. Okay. So so these are algebraic closures. So this is algebraic closure of Q. This is C is algebraic closure of R. Okay. So now with the help of this, what I was trying to prove, so obviously you can prove many things, but my goal was to give you that, and to prove that this kind of field exists also is not trivial, but one can prove that whenever you have a field, you can always find a extension which is algebraically closed. Okay, once you have a field which is algebraically closed, you take the subfield of that field which contains every algebraic element, and that will be algebraic closure. Okay, so without proof I am just writing these theorems because proofs are not so simple. So for any field if there exists k extension of F which is algebraically closed. Okay, and once you have that, then you find out that, then you define a bar. Obviously yeah, so you can define two ways. So okay, 1 minute. So for example, if you have R, then C will be that algebraic closed field, also algebraic closure, and I see if this is okay. So okay, so now remark, I should say remark here. So remark, if this K is algebraic over F, then K is the algebraic closure over F, right? Algebraic closure of F. If not, then what happens? If K is not algebraic over, so if this is algebraic, so if K is not algebraic over F, then what do you do? So you take the subfield, you take say F bar is so this is this all the elements of K such that this X is algebraic over F. Okay, and then we showed that this is always algebraic. Then this will be okay. So then this F closure this will be is algebraic over F. Okay, and you can find out this. Okay, so what does that mean? That means whatever field you have, you can have an algebraic closure. That is the most important idea. We want to use it for finite field. So in a case now what we are discussing, that the existence of this finite field with e power n many elements. Okay, so what happens? So you know that obviously if a finite field means the characteristic is P, right? Some prime P. So you have Fp sitting there, obviously, and then you take Fp bar is the algebraic closure which already exists. We know that algebraic closure. Okay, so if you have an algebraic closure, so I am saying that because so this is also a theorem that any two algebraic closure are actually isomorphic. I am not going into details everything. So this is algebraic closure of Fp, and now what you do, you take the polynomial, say fx equal to x power p power n minus x. Okay, and if this is the polynomial, and then you take your field. So I am defining this field Fp to the power n. So what is that? This is all the alpha belongs to Fp closure such that alpha f of alpha equal to 0. So alpha is the root of this polynomial. Okay, so if I take that thing, and then I will prove that this is a field containing p power n many elements. That I need to prove, right? So claim 1 that Fpn, this cardinality is p power n. Okay, okay, and then this field. So how to prove this cardinality p power n? So as fx splits completely over Fp bar, because this is a algebraic closure, right? So algebraic closure is also algebraically closed. So every element split completely there, right? So yeah, if x has p power n many roots in fp bar. But how do you know these roots are distinct? Now to show that, so if these are distinct, then you are done. If they are not, they may not be distinct, right? All there may be some roots repeating, right? So to show all these roots are distinct, what you need, you take that formal derivative. You see that if there is a repeating root, no, then the root will be again a root of the derivative, right? So for example, okay, so let me give an example first. Maybe somewhere here, let me write down here. So if a polynomial has a root of degree say 2, so f minus alpha square into some g dash x, hx, whatever hx, then you see that in g dash also you can write down 2x minus alpha into hx, this is hx, plus x minus alpha square into h dash x, right? So what does that mean? That means this x minus alpha is a common root, right? So x minus alpha is a common root. Common root means the GCD of x and x dash is not trivial. They have at least x minus 1 inside the GCD, right? So this idea I'm going to use it here. So you have this fx is x power p power n minus x, and then f dash x is what is the derivative of that thing? So p power n x power p power n minus 1, right? The derivative. Now you see that because this is a characteristic mod p, so this is equal to minus 1 in if p closer, right? Characteristic of that is p, right? So now check that this GCD of fx and f dash x, which is minus 1, it has to be 1. There's no other, the greatest counter is 1, right? So fx has no repeating roots, and hence that that field is exactly happy by many roots, right? Happy by many elements. Yeah, so this is exactly this. Now claim 2, this is a field. Oh yeah, so that I need to prove claim 2. Claim 2 that this fp, the way I define, is a field. Now to prove it's a field, you need to prove that addition and other things. But the most important thing, you need to prove that it is closed on the addition, closed on the multiplication, closed on the inverse. That is the most important thing. And then the distributive property, other property, you can prove it, right? Now how to prove this closed under those things? So let say alpha 1, alpha 2 belongs to this fp power n, and then you need to prove that alpha 1 plus alpha 2 belongs to that. So what does that mean? That means alpha 1 plus alpha 2 to the power p has to be alpha 2. But if we expand this in binomial coefficient, then what happens? This is alpha 1 to the power p n plus p power n choose 1, right? And then alpha 1 power p power n minus 1, alpha 2, and so on, dot. And then the last one will be alpha 2 to the power p power n, right? Now you see that in between all those entries, the coefficients are divisible by p, right? These are divisible by p, and hence they will be 0, right? So this is nothing but alpha 1 power p power n plus alpha 2 power p power n, right? But because alpha 1, alpha 2 element of p power n, alpha 1 by p power n equal to alpha 1, alpha 2 p power n equal to p power n equal to alpha 2. So thus this alpha plus, this is also true for plus minus also, doesn't matter. So whatever you write down, this is the element of p power n, right? Now similarly the product, so alpha 1 alpha 2 to the power p power n is nothing but alpha 1 to the, this is a subfield of this is a subset of the field, right? So commutative, so you can use that commutative property that to show that this is nothing but this, and again this is alpha 1 alpha 2. Okay, and for inverse you see that inverse also belongs to the set, because this power p power n is nothing but, so this is the inverse of alpha inside fp closure. Now I am saying that it is also inside fp power n, because this is nothing but, this is n whole inverse, right? Now what is this? This is nothing but alpha inverse. So you just say that alpha inverse to the fp power n is alpha inverse. So this is an element of fp power n, right? And then in the addition, multiplication, all those things you can easily prove, right? So thus fp power n is a field with this p power n many elements. Okay, and one more important thing I would like to ask, what happened to, how do you know that these so any two finite field are isomorphic? So let me write down. So the theorem any two finite fields are isomorphic. Okay, so the proof is also not so difficult. So let K be a finite field. So I will prove that any finite field or characteristic P is isomorphic to p power n for some n, right? So let this characteristics of a field, finite field is P, and this K over a P is actually some dimension is n. Okay, so we will claim that this K is actually isomorphic to isomorphic to a p power n. Okay, so how do you prove these things? So if I prove that the roots of that polynomial a p power x to the power p power n minus x belongs to K, you are done, right? So my claim is that K contains all the roots of this polynomial, which we already discussed, p power n minus x, right? Now obviously one root is x equal to 0 is one of the root that is already there in a field. Every field contains 0, right? So so what I need to prove? I need to prove that yeah. So we'll show that every element of K. So we'll show every element of K is a root of f of x, right? Now 0 is trivially true, right? Trivially a root of fx, right? Now if we have now let choose a non-zero element, so let alpha not equal to 0 belongs to K, right? Then we know that K, if K is a field, so if you take the non-zero element, they form a group, right? So thus alpha belongs to also K star or whatever, maybe write down K star, which is the group of non-zero elements of K, right? Now K star has order. What is the order of K star? P power n minus 1, right? And alpha is an element, so if you use the Lagrange's theorem, order of the element divides order of the group. So order of K divides P power n minus 1, and thus order of alpha divides this. So alpha power P power n minus 1 equal to 1, right? And that implies that alpha power P power n equal to alpha. So alpha, if of alpha equal to 0, right? So alpha is a root. So this is the proof. So every element of K is a root of fx, and K has P power n many elements. So what does that mean? That means it is nothing but K is actually isomorphic to a P power n. So any finite field whose characteristic is P and is isomorphic to a P power n for some n, okay, and hence any two finite fields are of same order. Any two finite field of same order, I should say. Finite field of same order are isomorphic. Okay. So if you are taking finite field of order 25, any two such things, they must be isomorphic to each other. Okay. So by this I am going to stop my lectures. Okay.